Hello and welcome to the lecture 1 of group theory. So group theory is a study of symmetries. Nature is full of symmetries, and in physics they come in various aspects. For example, in quantum physics, the system which is translational invariant has a momentum conserved. Similarly, in classical physics there's a theorem called Norris Theorem. Which says that if the Lagrangian, which is a function of the q dot, and possibly time, and here q dot means q1, q2, all the generalized coordinates up to n. So if the number of degrees of freedom of a system is n, then there are n generalized coordinates, and if the Lagrangian is invariant under the change of any of these generalized coordinates, then the corresponding momentum conjugate to that generalized coordinate is conserved. So if, for example, q3, if I change q3, so q3 goes to q3 plus delta q3, and so let's say it's q2, and if the Lagrangian is remain the same, so this is q1, q2, q3 up to qn, and I just write this q dot and t, and if this equals to Lagrangian q1, q2, and I change q3, and all that stuff is same, so this is qn, q dot, t, and if these Lagrangians are equal, then the momentum p3, which is equals to dl dq3 dot, then this momentum will be conserved. So the Norris theorem states that the continuous symmetries, so these generalized coordinates are varied continuously, so a Lagrangian is parameterized by these generalized coordinates, and if you vary any of the generalized coordinates and the Lagrangian remains the same, then the corresponding momentum conjugate to that generalized coordinates is conserved. So we will study these all applications of this group theory, but first of all, let's study the definition, the abstract definition. So let's define a group. Definition: let G be a set and star be a binary operation on G. That means a star is a map from G cross G to G. So it takes two elements, G1 and G2, and maps them to G1 star G2. And that element must be an element of the group. For this, that means it must be closure. So there are certain axioms. So first one is closure. It says that for all G1, G2 in the group, G1 star G2 must also be a group. So this binary operation must be closure. It must obey the closure property. So second one is associativity. So it says that G1 star, and then you do the G2 star G3, it must be equal to G1 star G2, and then you star it with G3. And this must hold for all the group elements in the group. And third one is the neutral element. So there must exist an element, so there must exist a unique element E in the group, such that for all elements G in the group, each star G must be G. So there must exist a neutral element. That means if you do the binary operation with any of the group element, it will then again provide you the group element. So it doesn't change the group element. And the last one is the inverse of every element. So the last one is the inverse. So it says that for all the group elements in the group, there must exist a G inverse in the group such that G inverse must be equal to the identity element. So every group element has an inverse. So now let's look. Now we have not stated any commutative property. Now if a commutative property holds, so for example, if an additional condition, let me put here a star, if an additional condition that G1 star G2 is equals to G2 star G1 for all G1 G2 in the group, if this property holds, then we say the group is commutative or abelian. Otherwise, all the group that does not follow this property is called non-abelian. So let's take some examples. So example, so the integers with the binary operation of addition is a group. So for example, if you take two integers, so let's say 1 and 3, now you just add them. 1 plus 3 equals 4. Now you added the two integers and it provided the another integer. So clearly the addition property, the addition binary operation is satisfy the closure property. Now the associativity 1 plus 3 plus 4 is equals to 1 plus 3 plus 4. So the associative property is also clearly satisfied by these integers. And for the identity for the neutral element, we have the 0. So for example, let A be any integer, and if you add 0, you again get the integer A. So 0 is clearly the neutral element with respect to addition. So the neutral element may change with changing the binary operation. For example, if you took the multiplication between the integers, then the neutral element would be 1. So you have to take into account what the binary operation you're talking about. So let's now take the inverse element. So the inverse element, for example, let A be any integer. Now clearly minus A is also an integer. So if you add them, A plus minus A is clearly 0. So for every integer A, there's an integer minus A. If you add them, it gives a neutral element. So clearly every integer has an additive inverse. So the Z with an binary operation of addition is clearly a group. Now, is it a commutative group or non-commutative group? So we see that if A and B are any integers, then clearly the addition commutes. So A plus B is B plus A. So yes, that's a abelian group. So this is an abelian group. So let's take another example. So example 2, real numbers, but I just exclude the 0. And that's a group with respect to multiplication. So first of all, the closure property. You know that if you multiply any two real numbers, then it again provides you a real number. So the closure property is clearly satisfied. So your closure is satisfied. Now associativity, if you multiply two real numbers and then you multiply with another real number, then clearly A multiply B multiply C. So this is clearly satisfied for all A, B, C in reals. So third property is neutral element. So with respect to addition, the neutral element, with respect to multiplication, the neutral element would be 1. So 1 times any real numbers again provides you with the real number. Now this holds for all A in the reals. So 1 is the neutral element with respect to multiplication. So fourth is inverse. So for all A in real numbers, there exists 1 over A, the reciprocal, which also lies in the real numbers, and if you multiply them, so A times 1 over A is again the neutral element. So for every real number, now this is not for every real numbers, I have 0 excluded. So you see, because if I included the 0, there will be a problem here because you cannot divide by 0. So only non-zero real numbers has a multiplicative inverse. So this holds for all A in only real numbers excluding the 0. So real numbers excluding the 0 is a group with respect to the multiplication, the ordinary multiplication. Now, is it a abelian group? Yes, indeed it is, because the multiplication is a commutative property. So A times B is equals to B times A for any two real numbers. So it's an abelian group. So let's look at another example, and that's a different one. This is the third example, and this consists of a set of n cross n matrices with real entries. So, and it's a group under operation of addition. Now clearly, if you add two matrices, you get another matrix. So for example, A and B are two matrices, n cross n matrices. So we can add them because they have both have the same order. So A plus B will also be an n cross n matrix. So it will also belong to this group. Now the second property, so that was first, it satisfies the closure property, and the second is the associativity. So if you add two matrix and then add with the third, you can just swap the brackets. So if you add first two matrix, then add to the third, it will give the same result. So addition of matrix is commutative. Now the third point is the identity element with respect to the addition. Now for in the set of all n cross n matrix, there's a matrix called the zero matrix. So all the entries of this matrix are 0. So if you add zero matrix to any matrix, it will provide you the matrix itself. So if you add A to the zero matrix, it will give you A. So zero matrix is an identity element of this group. And the third is, and the fourth one is the inverse. So this is with respect to the addition. So fourth one is inverse. So for all matrix A in this set, there's a matrix minus A. So for example, A has the elements Aij, n cross n, then minus A would have elements minus Aij, n cross n. So if you add these two matrices, so this is A plus minus Ia is equals to Aij, n cross n plus minus Aij. Now you can just add the elements together, so this will be a zero matrix, which is our identity element with respect to the addition. So for every matrix A in this group, there's a matrix minus A which also belongs to the group. such that if you add them you get the identity element. So this group is also abelian because the addition is also abelian. So A plus B, you can just swap them, you get B plus A. So it's an abelian group. Let's now look at another example. Because in mathematics, if you do lots and lots of examples, then you have a good understanding of the subject. So where this set is all those complex numbers such that they have a unit modulus. So if you have a pictorial representation that's a complex plane and all the points on this circle of radius 1, so this is real axis and this is imaginary axis. So all those points, all those complex numbers on this circle are in the set. And here, so for example, Z1 is one element and Z2 is another element. Now the Z1 in polar representation, it can be written as e to the I theta, where theta is this angle. So if you take the modulus of it, so this is U1 Z1 modulus, this is equals to Z1, take the Z1 squared, so Z1 times Z1 conjugate, so this is e to the I theta times e to the minus I theta. So this is equals to 1. So clearly every element of this type which lies on this circle has a unit modulus. So let's see if it is a group or not. So let's see, let's this be theta and let this be a phi. So let's multiply them. Z1 times Z2 is equals to e to the I theta times e to the I phi, and this will be e to the I theta plus phi, and theta plus phi lies somewhat, so this is phi and it lies somewhat here, so this is theta plus phi, so this is Z1 times Z2. So clearly the multiplication of two complex number on the circle lies again on the circle, so this is Z1, so that Z2 is also belongs to S1. So this multiplication on this set is a closure, so it satisfies the closure property. Now let's see the other properties. So associativity. So we have two complex numbers, three complex numbers, so Z1, Z2, Z3, and say S1. So Z1 be of the form e to the I theta 1, Z2 be of the form e to the I theta 2, and Z3 be of the form e to the I theta 3. So let's see Z1 times Z2 times Z3. So e to the I theta 1 times, so first you multiply these two complex numbers, so this is e to the I theta 2 times e to the I theta 3. So this is e to the I theta 1 times e to the I theta 2 plus theta 3, so which is equals to e to the I theta 1 plus theta 2 plus theta 3. So now let's put this bracket here. So let me erase this. So this is Z1 times Z2, you multiply with them, and then you multiply with the Z3. So this is e to the I theta 1 times e to the I theta 2, then you multiply with e to the I theta 3. So this is e to the I theta 1 plus theta 2 dot e to the I theta 3. So e to the I theta 1 plus theta 2 plus theta 3 So you see that the set under this operation is also associative. Now let's find out the identity element with respect to multiplication. Now let us assume an identity element zeta naught, and it is e to the I theta naught. Now the identity element has a property that if you multiply z naught multiply with the z1, it must again give you z1. So where z1 are led to be e to the I theta, the theta is in reals. So if I multiply these two, one e to the I theta naught dot e to the I theta is equals to e to the I theta. So this implies that e to the I theta naught plus theta is equals to the e to the I theta. So this is only possible if theta naught is equals to 0. So if I put the theta naught equals to 0, then this implies the z naught is 1. So this is our identity element, and it indeed lies on our circle here. So it lies here, so z naught is equals to 1. So this is our identity element, and it lies on the circle as 1. Now let's look at the inverse element. Now let z belongs to S1, and let its inverse to be z inverse also belong to S1. Now in the polar form, z can be written as e to the I theta for some theta, and z inverse can be written as e to the I phi for some phi. Now the condition for the inverse element is z times z inverse must give you z naught, and this is 1, which is equals to e to the I 0. Now z is e to the I theta times e to the I phi must be equals to e to the I 0 times 0. So this gives theta, so phi must equals minus theta. So this implies that I can replace the phi here with minus theta, and you see that this is indeed the complex conjugate of this complex number. So every complex number has an multiplicative inverse with respect to this binary operation, which is its complex conjugate. So and you can picture this on the complex plane as follows. So let's this be a theta and this be our group element, then its inverse would be its reflection with respect to this real axis. So here is real axis. So this is minus theta. So if you reflect every complex number with respect to the real axis, that will be its complex conjugate. So this is z inverse, and you multiply them, then you get identity. So yes, indeed, the S1 with respect to this multiplicative operation is a group. Now, is it a abelian group? Let's check. Now let z1 is equals to e to the I theta 1 and z2 e to the I theta 2. Now if you multiply them, you get e to the I theta 1 plus theta 2. But these are real numbers and they are commutative, so you can swap them. That would be theta 2 plus theta 1, and that indeed it is theta 2 times e to the I theta 1, and this is z2 times z1. So this group elements also commutes with respect to this multiplicative operations, and so this group is also abelian. So in the next video I will talk about some non-abelian groups and provide you further definition in this group theory. So thanks you for watching this video.